Hello and welcome back to this course on causality for psychologists and social scientists. You're actually at the end of the course now, the last section on sensitivity analysis. So let's get stuck in. So I presented to you this sort of conceptualization of this research process where we acknowledge that there's some complicated real world process, and that gives rise to a set of states, and it's difficult to capture really any one of those states completely. So we have sort of partial observability, where we go in, we create a questionnaire, and that questionnaire is effectively a measurement function that goes from the state of the world to a set of data. Once we have those data, we can perform analyses on them. In order to perform the correct analysis, we also need a theory about what this real-world process actually is in terms of its causal structure. And I said that this is one of the hardest parts of research, is getting a valid and useful theory, one that's a suitable level of abstraction from reality. And sometimes I think in psychology, we tend to err on the side of simplicity, despite the complexity of human behavior and human psychology. But that said, we also don't want things to be too complex, because then things become intractable and we increase the chances maybe that we've made a mistake in the theory. But once we've got this theory and we've specified it mathematically, formally, unambiguously as something that we can use to represent adequately the process in the real world, then we can follow a set of steps. They are the rules of DAGs, like I showed you before, and specify an estimand which is expressed in terms of the graph. We can identify that estimand from the data, hopefully, or we can run through that procedure, and then we can do the task of estimation to actually estimate that estimand. And this arrow here, I said, was relatively straightforward. It's sort of just a process of moving from the graph to identification. You either can do it or you can't do it. Here, the estimation is also sort of taken for granted, to the extent that if we have enough data and we have sufficient estimators, then that's not too difficult. But the real difficulty is really in this theory specification here. So what happens if we get something wrong in this process? And I think the chances of doing that are very high. That's part of why science is an iterative process. We keep updating our theories. And that's also another reason why we want our theories to be formal, so it's clear where the weak points are, where we need to make changes. But if this is wrong and we don't have causal discovery to maybe fix those problems, indeed causal discovery has many limitations, then what can we do to kind of hedge our bets and to make it clear and transparent that we're not putting all of our confidence in our model, to try and acknowledge the fact that this model is potentially imperfect? Well, this is where sensitivity analysis comes in. And the idea is that we give an estimate for how much our estimates are sensitive to mistakes that we made in this step here when we created our theory. So rather than pretending our graph and analysis is the only possible reasonable choice, it probably isn't, how can we quantify the sensitivity of our results, of our estimates, to mistakes that we've made earlier on in the pipeline? And I'm going to assume for now that we're good at this, going from the theory to the estimate and the identification, that we do that in a reasonable way. If you do identify weak points in that chain that are the reasonable weak points, that don't just stem from maybe a lack of knowledge about that process, but are genuine sort of research questions, then they can become part of this sensitivity analysis. But indeed, the idea is to try and quantify how much our result is sensitive to the mistakes that we've made early on in that research chain. And it also gives us a feel for the amount by which our adjustment set is doing good work to give us unbiased estimates of the true effect, to the extent that well, if adjustment isn't really doing anything, there's maybe a question as to whether or not those are really confounders. So it also gets us some idea of how valid our causal structure is, if we can sort of understand the extent to which using that causal structure to inform our analysis actually changes our results. It also helps us understand the degree to which ignorability is fulfilled. In fact, that's ignobility, which is not the word I meant. Ignorability is fulfilled, which is one of the key assumptions underlying the validity of our causal estimates. And in practice, it's probably never quite fulfilled, but we can try and understand and estimate the degree to which we have fulfilled it. So the process is to run at least 2 analyses. We start off with the backdoor block, so we include the proper estimate. We could even use the targeted learning approach we saw in the previous section to get these confidence intervals and the statistical inference out from the machine learning estimates. So we have this initial estimator or estimate psi hat 0. We then run the same analysis, but without including control variables, or at least we leave out some core control variables that we think maybe explain most of the confounding effect. And we're going to call this the naive estimate, psi hat bias. We can then calculate the difference between the naive estimate and the machine learning estimate, which will give us this sort of delta, the difference between the two. And that's actually going to help quantify the extent to which the confounders, which we do have access to, are influencing our estimate. Hopefully they're pushing it in a good direction, not a bad direction. And the difference actually corresponds with a conservative estimate for the maximum amount of bias possible and the model misspecification. The idea is that if we've done everything that we can to collect all the confounders that we can think of, then if we create two estimates, then the difference between them will capture the majority of the possible influence these confounders could have on our estimate. So it's almost like a worst case scenario. This naive estimate is capturing the situation when we did a really bad job of accounting for all the confounders. The assumption is that we have done a reasonable job in this estimate, and that any confounders that we've missed out can only contribute less than the amount by which, leaving all of the ones that we have has on our estimate. Excuse me. So when we compute then the difference between our complete estimate, our estimate for our complete estimate, including all these backdoor variables, plus some amount of this difference between the best that we can get and arguably the worst that we can do, then we can look at how the effect shifts for varying degrees of epsilon. So epsilon here is a multiplier determining the sort of amount of bias that we add or subtract from our estimate. So this provides different results for different levels of bias. So we can explore, for instance, what happens when we add 0.5 of the amount of bias that would occur if we didn't include any confounders, for instance. And then we can do this in various steps, and we can subtract and add, like we've got here, plus and minus. And so we can see at which point, what amount of bias would be necessary to render our effect consistent with a null hypothesis, for instance. So the results might look a little bit like this. So when we have no bias, this is assuming that we've got the perfect model. So this is our initial estimate, our best estimate here. We might estimate, for instance, for epsilon equals 0. So there's a 0 multiplier on that bias term. That our initial estimate is, say, I don't know, 0.17, something like that. And then what we're going to do is add varying amounts of this bias, plus and minus, and subtract varying amounts of this bias to our initial estimate to see at which point we actually overlap with the null hypothesis. So in other words, for this graph here, for this particular effect, I need 2.5 times the amount of bias that I adjust for when I do include the adjustment variables in order to get a null effect. So that's to say that of all of the variables that I've left out of my model, their contribution to biasing our estimate would have to be 2.5 times the amount higher than the amount by which we did adjust for in order to actually find a null effect, or for the effect to be null when in fact we found it to be significant. So this is a really useful way of quantifying the landscape of sort of how much bias we've adjusted for and how much could potentially remain. And one of the arguments might be, well, if we need 2.5 times the amount of bias that we've already adjusted for in order to sort of get a null effect, that's arguably implausible. Maybe you might say that, well, no, because we've done such a good job of collecting for all the confounders that we could possibly think of, we might argue it's not possible for the remaining or the residual confounding to be that large in magnitude. And so actually, you would argue that even under, say, 1 times the amount of bias that we've adjusted for already, if that's still significant, you might argue, therefore, that this is a relatively robust result, and that the fact that it's non-zero is a relatively reliable finding. So this is sensitivity analysis in a nutshell. This is a very short section. I really want to encourage people to start engaging with sensitivity analysis, to stop sort of putting all their eggs in one basket, arguing that they had the right idea from the start. There's a lot of opportunities to make mistakes when we're specifying our theory. There's a lot of opportunities to miss variables out. For instance, even if we're just looking at the relationship between smoking and cancer, we may try to collect lots and lots of confounders that otherwise explain the link between smoking and cancer, things like genetics or social circles or culture or whatever. And we might argue that in order for smoking not to explain cancer, i.e. for the effect of smoking on cancer to overlap with zero, we need an implausible amount of extra data, an implausible number of extra variables in order to account for the effect of smoking on cancer. So it's a nice way also to sort of judge the extent to which we're doing valid work with our observational data, as opposed to always needing randomized control trial data. For instance, if you find that when you leave confounders out, that it very quickly becomes null, you might argue that actually maybe we haven't included enough variables there. So it's something to consider. And as I said before, this isn't just about the DAG and whether or not you've left something out in your graph, but it's also maybe about mistakes made regarding the estimation process or anything else that you can think of where you had to make a decision and you said to yourself, well, I could choose this or I could choose that. I'm not quite sure which is best. That is a perfect candidate for maybe assessing the sensitivity of the resulting results to that decision. I think Andrew Gelman refers to this as the garden of forking paths. So every decision that you make along that research pipeline is an opportunity for you to get a slightly different result. And if you identify a certain decision as maybe quite a difficult decision to make, but potentially critical for the results, then I would encourage you to explore it and present the results under both of those decisions, particularly if one is not necessarily better or worse than the other. If you don't have a very clear right answer, that's a perfect candidate for assessing the sensitivity of your results to that decision. Okay. We've actually reached the end of the course. So if you stuck along this far, then fantastic. I really hope it was useful to you. I may add some things later on, but otherwise, thank you very much for watching.